Dear Mr. Chairman, dear colleagues, I would like to give you a very short presentation about the European project running and just closing next month for the Apal. This is advanced PT assessment for long-term operation of reactor pressure vessel. So it was a 4 years project, well, the main focus was to improve the PTS evaluation assessment of the reactor of the nuclear power plant. What you can see that in case of what is the point of in the case of reactor pressure vessels is a key component, both the water-cooled, water-moderated reactor vessel itself, and it's pressurized, of course. We have relatively high pressure inside, and we also have to provide a long integrity key issue and long-term operation. As usual, maybe you heard a lot of time that the nuclear power plant lifetime should be extended, and I would like to have a longer operation than the design lifetime. However, the vessel and its material is faced to the irradiation and embrittlement. So there is a degradation, aging issue that should be taken into consideration. However, we have to face to, or we have to be ready for some kind of circumstances. What is hopefully theoretically circumstance when we have a pressurized thermal shock on the reactor vessel, when we have to rapidly cool down and stop the reactor itself. But well, it's obvious that if we have to stop and cool down the reactor quite shortly, it means additional load, and this should be investigated. For PTS assessment, there is two kind of approach, let me say, or definition that what is come from the wildlife procedure. This is mainly for VVR and Eastern time reactors like VRA 100, VRA 100, 200, 1200, 400 reactors, and we have the US approach. Well, there are slight differences between the two, but the main issue, this is in both cases, the resistance of the RPV should be ready for against fast fracture. So it's not really acceptable at all. So it would be a very huge accidental issue in case of nuclear power plant. So what we focus on in case of characterization of PTS, a rapid cool down of a primary circuit. We usually we have a non-uniform cool downs because of the cold water comes to the nozzles. So we have a cold plumps or cold stripes or cold sectors compared with the other part of the vessel wall in the azimuthal direction. So and due to the emergency cooling system, injection system is asymmetric, and because of the cooling down by the steam generators, also asymmetric effect can be faced too. So and in this case, we usually we are high inner pressure because it's not unpressurized. It cannot be unpressurized, because if it's unpressurized, it's getting boiled. So because usually the PVR reactor, pressurized water reactors, we have a higher pressure, keep the water itself not boiling. So if it's getting boiling, it's getting even bigger problem. Usually in PTS we have a boiling issue as well, and the mixed phase flow issues. So and that's why we have high pressure and ununiform and unsymmetrical temperature condition, and means that the stress condition is asymmetrical. So and we have to theoretically that postulate defect in the reactor pressure vessel wall, because we should be ready to keep the condition if it has the defect. We have to deal with the loading condition and the cooling of the RPV, and also have to deal with the aging issues due to embrittlement of the pressure vessel wall. So if we have defect, if we have fast cooling, and if we have embrittled material, we have to analyze the issue against potential for fast fracture. So the main part is a kind of PTS analysis. It's very important, the thermohydraulic analysis when we have the system code analysis or the mixing code analysis. And after that, we have to carry out the structural analysis. After that, fractional mechanical test analysis. And after that, we have to carry out a deterministic and probabilistic approach to find out the condition of and the reliability of the reactor pressure vessel in case of PTS conditions. So in this project, we were mainly focused on the develop advanced deterministic and probabilistic method for PTS issues and qualification of the safety margin for long-term operation improvements, LTO improvements, and development of best practice guidance, what is still under development. In the project, we had 14 project partners from EU partners and 2 from outside of the Europe, from Oak Ridge, and the Japanese Atomic Energy Agency was involved, and UGV was the coordinator of the, or still the coordinator of the project. So you can see the structure. So if we started from the work package 1, what is the state of the art mainly, and after that, we have a work package for thermohydraulic analysis, deterministic margin analysis, probabilistic margin assessment, and after that, all the outcome is summarized in the best practice document. And also we have a training issues, training work package. So we have a final dissemination work package seminar, final seminar in next month in Paris, in middle of September. So what you can see, the current approach is we have a thermodynamic analysis, a deterministic, and from this we have a structural analysis, and after that from this we maybe have a probabilistic analysis. So, but the issues in case the condition for the thermodynamic analysis, I mean the boundary conditions and other circumstances, is rather probabilistic. So we should carry out a probabilistic thermodynamic analysis, and based on that, we should mainly carry out a probabilistic analysis of the PTS issue. And the safety analysis mainly focused on the against the core melting. That would be very important issue that as you can see that this is the new approach that shows. So in the work package 1, we carried out a very deep state-of-the-art review of the recent state-of-the-art review by questionnaring the partners and collecting the different approaches of the different countries of the project partners, and summarizing it and find out the gaps and carry out and determine the recommendation for the development. So we investigated the welding residue stress, warm press test, TH analysis, and the state-of-the-art probabilistic PTS analysis. This is mainly based on the previous ProSafe and ISAC project. And after that also the further the LTO improvements was taken into consideration how to what the plants should do to improve the lifetime and to reduce the effect for the aging and the unnecessary loads. So in the thermodynamic analysis, it was very important that not only the technical issues, but the human factor was a very high uncertainty issue that was taken into consideration. So as a pilot study, the KVU 1300 PUR was taken into consideration, and this geometry was mainly used, and several TH code and mixing code was used to analyze the thermodynamic circumstances. So this was carried out and was completed, and you can see the result here. And after that, the PTS deterministic margin analysis was carried out. In this case, we calculated the stresses due to the thermal issues And after that, the thermal issues was discussed and solved. Function mechanical analysis was carried out in the deterministic way. And further analysis was carried out because for VTS issue, what is the point? The tangent approach, maximum VPS approach, and the modified issue was taken into consideration. And you can see the result here, what how it was taken into consideration. You can, sorry, just 1 minute for it. For the mixing code, you can see the list of the plant parameters here that what was taken into consideration, what is the best emitted, what is the type of distribution, and so on. So that's also all the issues were taken into consideration for the probabilistic thermodynamic analysis. And you can see that for the outputs from the different analysis, you can well, just the color shows the best case, best estimate solution, conservative solution. Somehow it doesn't want to go ahead. And you can see this is a very, let me say, one of the final results, or when you can see that somehow the pointer doesn't show that. This is the Q1 curve and Q1C, and this is the result from the fracture mechanical assessment, the TH assessment. So if we don't cut the red dashed curve, we are on the safe side. Let me in a very simple way. So, but several cases should be investigated, and also for different approach was carried out, and yeah. And this is what we have now. This is a deterministic PTS cumulative distribution function of the resulting of the maximum available RT and DT data. And you can see that for the 3 different approach, what kind of result we have. This is not the final result of the project, but we are getting to the end of the project. But I don't know why it's not going. Go ahead. Oh yeah. So just this the work package 4 is under this currently running. So and we are waiting for the final result from this work package that should be completed by the end of this month. I mean, for this week, or by at least by the final seminar, because the project will finish by the end of September. So next slide, please. So and based on all issues, we will publish a best practice guidance that hopefully will be a useful document for the PTS analysis of the nuclear industry. So yeah, I guess next one. So thank you. I guess I can. This is a conclusion. What I said. I don't want to say so much about that, but because we're running out of the time. So and hopefully we'll get the final best practice document, and you will be able to use the outcome of the project. Thank you so much.